Hello and welcome to Chat with an Astronomer. I'm Laila. I'm a PhD researcher at the Argelander Institute for Astronomy at the University of Bonn. In this series, we would like to give you the opportunity to get to know some of the researchers of the IMPRS Bonn Cologne and some of their cutting-edge research work in astronomy and astrophysics. So my guest today is Maude Charmetant. Maude is a PhD researcher at the Argelander Institute for Astronomy. And before that, she studied in Paris and in Strasbourg and got a master's in astrophysics. Now she works on the so-called Sunyayev Zeldovich effect. It's a really mysterious effect. It's tiny. Maybe you have heard of it, but probably haven't, because it's not the most detectable thing. And right now in this conversation, I would like to get to the bottom of what it is, how we can measure it, and what it can tell us about what the universe is actually made of. Hi, Maude. You're a PhD student, a PhD researcher at the Argelander Institute for Astronomy. And I was just wondering, what interested you in astronomy at the first place? Why did you want to study it and become a researcher?
So I think what really interested me first is the fact that you can explain the world we live in, sort of. You can model it, you can predict it. You can really get a deep understanding of what is happening. And I thought that was mind-blowing. Yeah. It's really I feel like it's really the border of human knowledge. There is a lot of things we don't know in astronomy itself. And it's also a very wide range of scale, because you have particle physics at the very beginning of the universe, which is very small physics, where we know nothing about pretty much. And then you have huge scale with the biggest objects you can find, and you can really learn a lot about physics itself, I feel like, with astrophysics.
So you're really more interested in the physics behind it and those different events that are happening that are just completely different than what we know in our daily life usually.
Yeah, exactly. I think the really first thing which got me into it was when I was a teenager, during holidays I would go to the beach or to the swimming pool, and sometimes you don't really want to swim, so you buy magazines. And I bought a magazine on science, and in one of those articles they have, it was about gravitational waves. And I'm not working on that at all, but I remember reading about, just the fact that masses modify the space-time shape, that it deforms it, and just I never thought about that before. I never really realized, okay, how does that work? How does gravity works? How does masses affect stuff? Things that we can't even really observe by eyes.
Yeah, there's so much more out there to learn and to understand.
Yes.
Than what we see every day. Yeah. And luckily, you're now actually one of those people that try to understand what the universe is made of, what is happening, all those different phenomena. So what exactly is your research topic? What is the effect you're working on?
Yeah, so I'm working on the Sunyayev Zeldovich effect, that we usually
It's a really complicated name.
Yeah. We usually call it SZ, like that. It's more simple. So Sunyayev is a Russian researcher, and Zeldovich was a Russian researcher. He was the thesis advisor of Rashid Sunyayev. And so they worked together on a different topic, I guess. I don't know in detail, but together they published in the 1970 exactly, a paper about this effect, which is now called the Sunyayev-Zeldovich effect. So this effect is actually a collection of effects. There is many different flavors of this effect. But all of those SZ effects are based on the fact that the photons coming from the very first light of the universe, so very far away in the past, very far away in distance compared to us, when they travel through the universe, to reach us on Earth with our big telescope. Sometimes they pass through a structure, and sometimes they pass through a galaxy cluster, which is a collection, a collection of galaxies. And between those galaxies, there is very hot gas, ionized gas, which means that there is free electrons, particle moving around. And it's very, very hot. And those photons, because they come from so far away, they lose a lot of energy. So when they arrive, they have very low energy, and they're going to scatter on those very hot electrons, and they're going to gain energy because of that interaction with the very hot electrons. So the SZ effect are the fact that we see a modification of the photon's energy coming from the very first light of the universe, which we call cosmic microwave background, because they interact on those hot electrons in a galaxy cluster.
So it's sort of like on a billiard table when
exactly.
one ball gets against the other one, and then it gets a little bit faster.
Yeah, that's a very good image. Thank you. Yeah, exactly. Yeah.
Okay, so the universe is made up of a lot of billiard balls in galaxy clusters.
Yeah, you could say that exactly. It's really hot and dense, and they're moving really fast. So yeah.
So you talked about the cosmic microwave background. So that's the first light in the universe. What exactly is that?
Yeah, sort of. I guess you could say it's the first light. To explain it, you need to explain a bit the history of the universe. So I think most people know that we think the universe started in a very dense and compact state that we call the Big Bang, and then it expanded very fast and became really big in a very short amount of time. We call this phase the inflation phase. And after that, the universe kept expanding. So after the inflation phase, it was basically a very hot and dense gas, you could say. Well, it's actually a plasma because it's ionized, but just to get an image, it's basically like a gas. So there were a lot of particles moving around, very hot, very energetic, moving really fast. And free electron, exactly like in galaxy cluster, free electron moving around. So the photons, which are the light particle, they scatter on those electrons, so they get absorbed and re-emit. But the problem is that it was so dense and so hot that as soon as the photon would escape the electron, sort of, it would get absorbed again. So the photons, the light particle, they were sort of trapped in this very hot and dense gas, and they could not escape. So we say that the universe was opaque because no light could really get out of this dense phase.
That's it, like a really dense soup or something like that. So okay.
Yeah, exactly, like super dense soup where you could see nothing. Sometimes an image that is chosen is, for example, miso soup, which is like a bit opaque and like smoky, I would say. So you really don't see anything. Then the universe continues to expand, and when a gas expand, then it cools down. And that's basically what happened with the universe. It became cooler and cooler, and at some point it was cool enough for atoms to form, which means that the electrons that were moving freely around before, now they were trapped with the nucleus. So they form an atom with a proton and a neutron, for example. So they were stuck in an atom form. And because of that, they were not moving around freely anymore. So the photons were able to escape. For the very first time, they would not get absorbed anymore by the electron. So they were able to escape, and that's the first light we can see, actually. Because before that, the universe was not transparent. The photon could not escape. So that's what we call the cosmic microwave background.
So it's like a baby picture of the universe when it was really, really small. And now we see it.
Exactly, yes.
Yeah, and so you study this light, the CMB light, and you see where there is this set effect, so where you have some different photons, some photons that have additional energy, right?
Yeah, exactly. So when you look at the CMB itself, so the photons coming from the CMB, they're supposed to be at 270 Kelvin today. But yeah, when they pass through galaxy cluster, they will interact with the hot electron and they will gain some energy. So actually, when you look at the microwave sky and you look at the CMB itself, you can see a difference in energy due to a difference in temperature, due to the fact that those CMB photons have interacted with the very hot electron in galaxy cluster.
Is this a really big effect? So do you see it a lot, or?
No, it's actually really, really small. So first you need a photon to pass through a galaxy cluster, which is really not the majority of them. And then on top of that, as I said, there is different type of SZ effect, different flavor. So I think the most common SZ effect is the thermal SZ effect. So in that case, it's really the CMB photons gaining energy when they interact with the very hot electron in the intracluster medium. So that effect is around 100 microkelvin. So that's 10 to the power minus 6 compared to the CMB temperature, pretty much.
Oh, wow.
So it's really, really small. Yeah. And then you have some other SZ effect, for example, the kinematic SZ effects. So it's the same idea again. It's the CMB photons that scatter, that interact with the electrons. But this time the electrons, they are moving. It's when the photon will scatter on a moving electron, actually. And then you get an additional effect due to the velocity of the electrons. So yeah, in this case, that's what we call the kinematic SZ effect, and it's really small. It's even smaller. It's 10 microkelvin, so it's 10 times less than the thermal SZ effect, which make it really, really small.
Really small, really small. Yeah. So that's a really tiny effect, but still, it's interesting and to study it. So.
Yes, so actually I've heard that apparently Sunyayev and Zeldovich, especially Zeldovich, he didn't want it to publish this paper about the SZ effect, because he thought, oh, this is so small, it will never be detected, like no one will ever see it.
Oh.
But, yeah, that would have been really sad.
Okay, but good thing that they did publish it.
Yes, because nowadays with technology, and that's really amazing, we are able to detect it and to do, actually, even if that's a very small effect, to do very nice science with it. So that's really amazing.
So what can we use this effect for?
So we can actually use it for quite a lot of different things. So we can use it for cosmology first. So we can constrain different type of cosmological parameter, which are like the parameter that characterize our universe, I would say.
So we can actually find out how the universe looks like in itself. So like how it's expanding, what it's made of, and
really exactly. Yeah. And then you can do more astrophysics related stuff with it. So for example, you can measure temperature in cluster. Also very basically, you can count cluster, because then when you look at the sky, you will see at very low frequency, so low energy, less photon than you should. Because those photons, they have gain energy interacting with the hot electrons. So whenever there is a cluster, you will see a deficit, so less energy at low frequency and more energy than you should at very high frequency, so high energy. So yeah, using that, you can then see, okay, there is a cluster here, there is a cluster here, and then you can count them basically.
Oh, and also it's really nice to know where there are these galaxy clusters.
Oh yeah, you're right. You're absolutely right. It's very good to know where clusters are, because For example, then if you want to study them in detail, sometimes you need specific studies or specific telescope that cost a lot of money, and they don't. They have limited time in a day. There is only 24 hours. So you really need to make sure, okay, if I want to use this very specific technology or telescope to observe a cluster, you want to make sure, okay, it's here, and if I put the telescope here, I will see the cluster and be able to deduce something from it.
Yeah, so that's really, really useful effect. So when you do your research, how do you do your research? Because you cannot really go to a telescope and then observe.
Yeah, there is a few, there is a space telescope that did the SZ effect, like Planck, for example. And there is some future project that we do SZ on the ground, actually, because now the technology is getting so much better, and even with the atmosphere, we might be able to detect it from the ground. But myself, I'm not like observing the SZ effect from any like ground-based telescope or using a space satellite. I'm working on a simulation. So using computers, we can simulate like how the universe would look like, and then how the SZ effect would look like depending on how the universe would look like. So
you recreate the universe in the computer, basically.
Yes, some people do that, and that's also amazing. That's an amazing part of astrophysics. I think it's like being God a bit, you can reproduce the universe in a box. We are able to do that. Of course, it's not perfect, and it's quite amazing. So there is some people who do those simulations, and then they make it public for everyone to use. So basically, I use their simulation of like how the SZ would look like on the whole sky to do science with it. Yeah.
Okay, and then you can compare what gets out of the simulation with the actual real world, and then you know something.
Yeah, exactly. So, for example, one of the future telescopes that will observe SZ, CCAT Prime, will be built on the ground in Chile. And I'm making prediction using simulation of what maybe this telescope will see in terms of a Z effect, if it will be able to detect it or not. So that's really those kind of stuff I'm doing right now. I'm trying to predict which type of result we can get from a simulated telescope, sort of simulating the sky this telescope might see.
That's really, really fascinating. And the whole range you can do with this effect, even though many people have never heard of it, and even though it's tiny, it's still really, really useful.
Yeah.
Just a final question that I wanted to ask is, what is it that you like the most about being a PhD researcher?
So I would say probably the fact that you learn something new every day. And also what I like a lot is that you have to teach yourself, sort of. Sometimes you really run into the situation but sometimes, you read an article or something and there is, I don't know, a definition you don't know, a set of simulation you've never heard of, and then you need to go yourself, look for it, try to understand what they did. And it really brings something to your knowledge. Then you basically build it little by little. And I think that's really, really interesting. Also, there is the fact that you participate to building new knowledge for humanity, and it sounds super. Yeah, but I like that a lot, to think that you can be a part and really bring something. So I think that's really important to explore our world and try to understand it. I guess that's one of the things that make us human.
Yeah, really, it's part of humanity to be curious and to try to understand what is going on, and just expanding this sphere of knowledge that we have just a little tiny bit. That's that's a really good purpose.
I think so.
Yeah, so thank you very much for this conversation. I had a really good time.
Thank you, Laila. That was very nice.
So that was a really lovely conversation with Maude. Thank you very much for that. I especially like the image of the universe in the beginning being like a miso soup, a really thick, mostly delicious soup, from which the whole universe actually formed and all the things that we know. And what about Maude not being that interested in pretty pictures, but more in the actual physical effects behind astronomy? That was really fascinating as well. So just expanding the sphere of human knowledge is her goal, and that's a really, really laudable goal. So thanks again, Maude. And if you'd like to see more of these interviews and conversations, click to subscribe, hit the notification icon, and you will get notified as soon as another one of these is up. Thanks for watching.